Well, today we'll introduce general relativity to you from the very beginning. Beforehand, we have discussed review of special relativity and some concepts related to gravitational field, such as gravitational redshift. But right now, today, we're going to enter into the formalism of general relativity. Okay, Einstein's approach to gravity, Einstein's approach to gravity is that the flat 1 plus 3 dimensional, 1 plus 3 high, 1 time dimension, 3 space dimension. 1 plus 3 dimensional Minkowski spacetime should be replaced by an appropriate curved spacetime, and the curvature shall be the cause for gravitational effects. Curvature is responsible for gravitational effects. Then comes, how do you visualize the events? Events in Minkowski spacetime, a point which have 4 coordinates t, x, y, z. In curved spacetime also events will be points and will have coordinates t, x, y, z. And to have proper dimension, ct, x, y, z. This will be the same as Minkowski space. But the relationship between different events and between different inertial observer will be different from that in Minkowski space, because now the space is not flat. The space is not flat. The space is not curved. So the relationship between events, one relationship we can write the in Minkowski ds square is equals c square dt square minus dx square minus dy square minus d square. This will no longer be valid. So this is also, this Minkowski ds square is also a flat space-time property. This is also entails flat space-time. This is not curved space-time. So relationship between events will be different. Okay. Now the question is, can we define vectors, coordinates, etc., those familiar concepts which we deal in Newtonian mechanics? Can we define such vectors in curved spacetime? This is the question. Now, and we say that imagine that this is the curved spacetime. Okay, if this is the curved spacetime, is there a finite vector here? A vector has a single direction, right? But here, if a vector is here, its direction will go this way, but the space is curved. So direction in a curved spacetime lose meaning. You cannot extend your direction throughout the space, but in flat spacetime, direction is at infinitum. From here to infinity, you can choose a direction. But in curved spacetime, you cannot define a direction beyond certain point. What is that point? Say, this is curved spacetime, here is the point. In the vicinity of that point, take a small region. Take a point in the curved spacetime. At a point, consider a small surface around it. Actually, that surface is what? That is a surface which is tangent to the curved surface at that point, and is part of a surface, a plane which is tangent plane to the point on the surface. Here, tangent. So, in a curved space-time, at a particular point, you take a small region. In the small region, vectors can be defined because direction has meaning there. In the small, you can define direction. But in curved space-time, in the large, you cannot define direction. But in the small, you can define. And that definition depends upon the taking of an appropriate area around a particular point and making sure that that plane, that area is really reside over the tangent plane. Okay, good. Now, what about this relation? How would we would modify this? What is this actually? This is actually generalization of the three-dimensional displacement spiral. In three-dimensional displacement spiral, you have what? Say we have only x, y, z coordinates. X, y, z coordinates. The displacement spiral is what? dx square plus dy square plus dz square, right? In Minkowski space-time, we have additional c square dt square, and signature is different. What is signature? Signature is the signs before the terms. In special relativity, the signature is like +1, -1, -1, -1. This is the signature. So if you say that I will count the trace, then signature will be -2. Signature will be -2. So Minkowski space-time is a space-time of signature -2. Okay. So how would we modify that relationship of three-dimensional space-time and of that of Minkowski space-time? For this, to do, suppose a curved surface is supplied with curvilinear coordinate system. A curved surface is supplied with a curvilinear coordinate system. See, this is a curved surface. This is a curved surface, and in this space we are supplied with two curvilinear coordinates. One is u, another is v. U, v, two coordinates. This is a plane, two-dimensional surface. Two-dimensional surface, not plane. Two-dimensional surface. In this two-dimensional surface, in this 2D surface, we are supplied with two coordinates, actually curvilinear coordinates, u, v. Now say I have a finite displacement dr. Infinitesimal displacement dr. I have infinitesimal displacement dr. So how do you apply the Pythagoras' parallelogram theorem? In Pythagoras' parallelogram theorem, in a triangle, the two sides, the base and the tangent, are appropriately added to give the hypotenuse. Now here I have the hypotenuse dr. So what will be u? U will be parallel to this. So you cannot go too far. You cannot go too far. So this you can go this far and along the u direction. This is the u direction. This is the v direction. And then parallel to this, and we call this is dr. We call this a vector du, b vector dv. The small changes, the small two changes are a du plus b dv. A is the vector which is defining the direction at that point. This A is unique for that point. Say this point is P. A and B are unique for that point. If you go at another point, A and B will be different. So unit vectors, actually they are not unit vectors, but they have magnitude 1. They have magnitude 1, but they are not actually called unit vectors. So, what will be dr? We have dr equals a du plus b dv. Just as parallelogram theorem of Pythagoras, but applied in the curved spacetime. Okay. So, where do A and B reside? A and B reside on the tangent plane at point P. A and B reside on the tangent plane at P. So that A have a meaning, B have a meaning as factors. Because that direction can be preserved there. Okay. Now take two vectors. Take two vectors dr1, dr2. dr1 is a du1 plus b dv1. dr2 is a du2 plus b dv2. Why so? We have said beforehand that point to point the relationship between equations will change. So UV will not be unique for all points. For dr1, this is d1 dv1. For dr2, this is d2 dv2. But both of these 2 points are to be at the same place. In that case only you have meaning for A and B. In that case only you have meaning for A and B. Right? So, now if we do the vector product of this, now the scalar product of this, actually scalar product is also a vector product, but what it gives you the scalar result, dr1 dot dr2, you can write this A du1 plus b dv1 dot A du2 plus b dv2. Then you can write, say, I should not fill out all the calculation, and this is the row matrix du1 dv1, this is the row matrix, then a square matrix 2 by 2 a square a dot b square, then this column vector du1 dv, du2 dv. Okay, I invite you just multiply these two terms. These two terms by these two terms, taking account of the vector dot product. We will find an expression. That expression can be written as this. That expression, that multiplied result, can be written as this. What? Of a product, matrix product. These are row matrix, a square matrix, a column matrix. So we write this actually in this way: du1, dv1, g, du2, dv2. What is G? What is G? G is the two-way matrix S square N dot B N dot B square. G is this two-way matrix. Now, what is this component? What is this component? We label them by the coordinates. This is U, V, this is U, this is V. Then what is this? G, U, U. You guys are S square. What is this? G, U, V. What is this? G, V, U. G, V, U. Both have magnitude, both have the same value, and V. And what is this? G, V, V. And this is this guy. So we call these are the components of the G, and G is called the metric tensor. G is called the metric tensor at the point P. G is called the metric tensor at the point P, and it has components GUU square, GUV, GVU, and B, GVV equals this guy. It has these components. So in this way, the simple mean basis spacetime has emerged or migrated from its simplicity to a complex world of general relativity. What? In special relativity, what are the things? C square, dt square, minus dx square minus dy square minus dz square. The values are either 1 or minus 1. G values are either 1 or minus 1. But in curved space-time, the values are not so simple. Okay. Now, what about a little bit more about another vector? Displacement is not the only vector. At a particular point in curved space-time, you may have to define velocity, force, acceleration, etc. Right? Because you are dealing with mechanics. So at a particular point, you can have to define not only coordinate or displacement, but force, acceleration, velocity, etc. These are usually not always infinitesimal vectors. These are little bit more. These are finite vectors. Okay, no problem. Finite vectors also can be expressed by using A and B, the two direction vectors. A and B are two direction vectors. You can use A and B and define any vector at a particular point. Say I have a vector V. I'll write it as capital because previously I have used V small to define the coordinate. Now to define a vector, I should write V vector. And this will be given by the contravariant component VA, VE. Actually, this is not the case. We have to write here VA, VB, the contravariant components. In the literature, I'll supply you. You will find VAB and as suffix. But right now I'm writing as superscript because actually these are superscripts. Why? These are called contravariant components. For contravariant components, the suffixes appear on the top, superscript. So a finite vector V has components VA, VB. These are contravariant components. Contravariant components. And V can be explicitly written a vector VA plus V vector VB. Understood? Okay, we shall now deal with an example. Say the surface of a sphere. The surface of a sphere is a curved surface, right? The surface of a sphere is a curved surface. So draw a sphere. Draw a sphere. Okay? So here is the center and this is the equator. Right? This is the equator. Here is the center. This is the North Pole, this is the South Pole. And angles in this, a point here, theta phi. And lengths r. These are actually the radius of the sphere. Do not think that I have pointed here, so this is less than the radius. No. This point is on the surface, and the radius of the surface is r, capital R. So this is capital R. This angle is theta. Theta is called co-latitude. Actually, latitude is called this angle. So this angle is called co-latitude. And say you take a projection over the equator and get the angle phi. Phi is called longitude. These are familiar concepts in curvilinear coordinate system, right? In curvilinear coordinate system, these are defined also this way. Now, if a small change d theta is taken, it will produce a shift of the point on the surface as r d theta. Understood? A small change in the theta will produce a shift on the plane r d theta. Similarly, for d phi r sin theta d phi r sin theta d phi, right? Because r has to have the component on the equator, that will be r sin theta. Then along this direction the shift is r sin theta cos phi. d phi, cos phi, not d phi. The small change. So this change d phi. R sin theta d phi. Okay. These two changes, shifts or changes, produces a finite displacement, right? What we call ds. What will be ds square? ds square will be r d theta whole square plus r sin theta d phi whole square, right? Do you agree? Is equals r square d theta square plus r square sin square theta d phi square. Then what? Then what? G theta theta. What is this? This is the first term. D theta theta. Because d theta comes twice here. D theta multiplied by d theta. D theta comes twice here, so we got this theta theta component. The d theta theta is what? R square. Do you have any term d theta defined? No. So g theta phi equals g phi theta equals 0. And this what? This is g phi phi. This is r square sin square. Understood? So in this way we have mastered the minimum of differential geometry which is required to study general relativity. In general relativity, what is the most fundamental thing? The metric tensor. G is called the metric tensor. The term what we are using here, G, it is metric tensor. This is not the acceleration due to gravity. This is metric tensor, and it defines the property of space-time. Around say around Earth, there is a g theta, g. Around Sun, another g. Around a black hole, another g. Every object has a g around it, because every massive body makes a change in the atmosphere, change in the space-time around it, change in the space-time around it, and that change is entailed, imprinted in the quantity called G, metric tensor. Here, these are components of metric tensor. Components of metric tensor. For what? For a sphere. Right? Understood? So today this much. Next class will advance toward more complicated things. I hope that will not intimidate you. Thank you.